Right, this lecture is we are going to introduce L'Hopital's rule. And basically, L'Hopital's rule says that if we assume that f and g are differentiable on an open interval containing a, and that f of a equals, sorry, this is terrible, that g of a is 0, we also assume that g of x is not 0 except possibly at a, then we can say that the limit as x approaches a of f of x over g of x, right? If we, based upon this, this would give us a 0 over 0, right, case, essentially. And that would mean that we'd have an indeterminate form, which meant that we had to do a bunch of algebra. But now this gives us a new way to evaluate indeterminate forms that basically says, okay, well, if I get 0 over 0 here, then this is the same. I can evaluate the limit by taking the derivative of the top over the derivative of the bottom. And if this limit exists or is infinite, then that's the limit of this one. So it's kind of a really nice rule for us now, so that we have some of those 0 over 0 cases that we had so much algebra for, we can now use this. And so it uses, so basically this definition up here is basically for the 0 over 0 case, but it also works for other indeterminate forms, and these are kind of a list of all the different indeterminate forms here. Sorry, my paper's getting all... So basically it'll also work if I have infinity over infinity, and then also if I have 0 times infinity, infinity minus infinity. Now there's some algebra that goes along with these. These are, I'm going to put these in a second lecture. And then also these 0 to the 0 power, 1 to the infinity power, infinity to the 0 power. These three kind of are special cases where they can we can use L'Hopital's rule on it, but usually we have to take the log of both sides first. So it's kind of like our logarithmic differentiation, except for this time we're going to use it to solve limits instead. Okay, so we're going to start out with kind of the basic cases of 0 over 0. Okay, so maybe this one looks familiar to you because we had this as one of our special cases when we were doing trig limits before, and hopefully you recognize it, and this should be equal to 0 because we had the two of them, right? We can actually do the other one too. So we had the limit as x approaches 0 of sine of x over x. We knew that that one was 1, and then this was the 1 minus cosine of x over x, which was equal to 0. So if we plug in 0 here, now this matters, we have to check it. So if I plug in 0 here, then if I write these out separately, the limit as x approaches 0 of 1 minus cosine of x, this is actually equal to 0, right? Because cosine of 0 is 1, and the limit as x approaches 0 of x as x approaches 0 is also 0. So this is a 0 over 0 case. I'm trying very hard not to write that this is equal to 0 over 0 because I've been grading for AP Calculus, and that is a major sin in their eyes. So we don't write that this is equal to 0 over 0, we write that it's a 0 over 0 case. Or we could do like that's 0, but we don't write that it's really equal to 0 over 0, so try not to do that. All right, so now we know that we have a 0 over 0 case, which fits our definition of L'Hopital's rule, right? Because we knew that f of a is equal to f of a and g of a were both equal to 0. So when I looked at this limit and I tried to plug in a, I got a 0 over 0 case, okay? So that means that this then we can use L'Hopital's rule, right? Because now this applies. Now, the book doesn't do this, but I would really like it if you could at least tell me that you are doing L'Hopital's rule. So like what I usually do is I'll do basically LH, right? So then I'm going to do the limit as x approaches 0 of, now this is kind of nice. Now this is one case where we're not going to actually use the quotient rule. We're going to do the derivative of the top, put it on top, the derivative of the bottom, put it on bottom. So the derivative of 1 is 0. Derivative of negative cosine will be positive sine, right? Because the derivative of cosine is negative and it's already a negative in front, and then over 1. So now I just have the limit as x approaches 0 of sine, and there is no reason whatsoever in which I can't put the 0 in here now, and so the sine of 0 is equal to 0, so that means I just essentially proved what we kind of were memorizing before, that this was equal to 0. Right, so this limit is equal to 0. We used L'Hopital's rule to show it. So before we get too far here, actually, let me just do the sine of x over x case really quickly. So, right, if I plug in 0 on top there, then I get 0, and I get 0 on the bottom. So I don't really need to show the separate limits. I know that I have a 0 over 0 case, right? So basically this is a 0 over 0 case. And so I'm going to apply L'Hopital's rule, which says that then the limit as x approaches 0 of, I'm going to do the derivative of the top, which is cosine. Derivative of the bottom is 1. And now I just have cosine, and when I plug in 0, cosine of 0 is, in fact, 1, right? So now, if we forget, now we have a way to come up with it. Okay. All right, so next case. Sorry, I got a little bit. So here's my next case here. I have, now, it doesn't matter, like I said, sort of in the definition of L'Hopital's rule, I said as x approaches a, but it also applies for x approaching infinity or negative infinity too. So it doesn't just have to be a number. Right, so if I plug in infinity here, right, so in the bottom, let's actually write these out separately. So the limit as x goes to infinity is 1 over x, or I'm sorry, I wrote that wrong. The limit of x as x approaches infinity of 1 over x. If I plug infinity in here, then I get 1 over a giant number, which in calculus we say is 0. And so then if I have the limit as x approaches infinity of, let's do the top, e to the 1 over x minus 2. The only thing that is affected by the x is this, right? And we just said that the limit as x approaches infinity of 1 over x is 0. So basically, this is equal to 2 to the 0 minus 2. Or actually, 2 times 1, right? Because this would be 2 times e to the 0. So this actually gives me 0 because I end up with 2 because this is e to the 0 power, really, when I take the limit, so that is 1. So 2 times 1 minus 2 is 0. So basically, I have a 0 over 0 case, which means I'm allowed to use L'Hopital's rule on it. Okay, so now we're going to L'Hopital it. I didn't leave myself nearly enough space, so let's do it like this. All right, so my L'Hopital's rule, I'm going to use the limit as x goes to infinity. I'll put my LH there. All right, and so now I'm going to take the derivative of the top separately. So this 2 is going to vanish, right? And then the derivative of 2e to the 1 over x is the derivative of anything with e in it is always the same thing. So I get 2e to the 1 over x, and then times the derivative of 1 over x. So that's x to the minus 1, so its derivative is negative 1 over x squared, or negative x to the minus 2 if you'd prefer to write it that way. Okay. And then on the bottom, I have the derivative of 1 over x, which is exactly the same thing. Okay. So now if I plug in infinity, right? Well, actually, I don't want to actually think about plugging infinity first. I want to simplify my algebra first. And I can see that this and this are essentially the same thing. It's all multiplication. I'm allowed to cancel it out. So what I really have here is the limit as x approaches infinity of 2e to the 1 over x. And since we've already shown over here that the limit as x approaches infinity of 1 over x is 0, this ends up being 2e to the 0, which is just 2, because anything to the 0 power is 1. Okay. Next example. Maybe you recognize these from, was that done the first test or the second test? I'm not sure, but these were the trig limits that we had to use the sine of bx over bx was equal to 1 to do, but now that we have L'Hopital's rule, we don't need it anymore. Now, just to make sure that I can use this, I plug in the 0, I get the sine of 0 over the sine of 0, and the sine of 0 is 0, so I have a 0 over 0 case, which means I'm allowed to use L'Hopital's rule. This really does matter, making sure that we can use it. Okay, so using L'Hopital's rule here, I'm going to take the limit as h approaches 0 of, so I'm going to do the derivative of sine of 2x, so that would be the cosine of 2x, then times the derivative of the inside, which is 2, which I'm going to put in the front, and then the derivative of sine of 7x is cosine of 7x, and then times the derivative of the inside, which is 7, which I'll put in front. Right? So now this is equal to, now when I plug in 0 into cosine, I don't get zeros anymore, right? So I'm going to get 2, I'm not saying limit anymore because I'm putting in the number, so 2 times the cosine of 2 times 0, which is just really the 0. So 2 times the cosine of 0. And then this is 7 times the cosine of 0 as well. So cosine of 0 is 1. So essentially I have 2 over 1 times 7 over 1, which gives me 2/7. So a lot easier than using that whole manipulation before. All right, so those were some 0 over 0 cases. So let's look at some infinity over infinity cases. Okay, so we've looked at these, depending on which class you're in, a couple of different times, right? So if I look at the limit as x approaches infinity, I'm really looking for the horizontal asymptote of this, the end behavior of this rational function. And if you recall, by doing those maybe multiple times, when I have a case here where the leading, essentially, I can kind of look at this and see the limit here because I have a second degree polynomial over a second degree polynomial. And when the powers, the highest power, the degrees match, then it's the ratio of their coefficients. So what I should get out of here is -4/3 because my ratio of my biggest things are 4 over -3. Okay. So, but when I plug in, and if I just was looking at them separately, if I look at the limit as x approaches infinity, I'm just kind of giving us, we've seen this before. If you don't remember that, then this is a good way for, in case you forget. Okay, so if I look at the limit as x goes to infinity of 4x squared minus 6, this is a polynomial, which is going to shoot off into infinity, right? It's a quadratic, it's up, up, it's going to basically go to infinity. Now, technically, it's really not equal to infinity, but we still write it like that. So then if I look at the limit as x approaches infinity of 9 minus 3x squared, this is likely going to negative infinity because the x squared is here as negative. But in any case, whether it's positive infinity over positive infinity or negative or it doesn't matter, the signs match. But essentially what we have here is an infinity, oh, that was a terrible infinity sign, infinity over infinity case. Now what we really have is infinity over negative infinity, but the signs are irrelevant. As long as I have an infinity on top and an infinity on the bottom, that means I can use L'Hopital's rule, right? So now it's really going to be easier for you in the long run, especially if you need to take Calc 2, to be able to see this limit, but we're just going to use it in this case just to show it still works, okay? So the limit as x approaches infinity, I'm going to use L'Hopital's rule. So I still have the limit as x approaches infinity. Oh, I cannot make infinity symbols this morning. So I'm going to do the derivative of the top. So that would be 8x. And then in the denominator, I have, so the 9 is 0, and then I get -6x. And so now really I can simplify here and get 8 over -6, which is in fact -4 over 3. So just in case, right, we can always see this. When it gets to be, if it's just quadratics, that's not a big deal. But if I had like 4x to the 4th over -3x to the 4th, I'd have to do L'Hopital's rule a couple of different times, probably before I got to the end of it. But I can use it if I have infinity over infinity or negative infinity over negative infinity or a positive in the top and negative in the bottom and vice versa. All right, so here's one that I can't really see. Now, I'm not sure if I said it explicitly before, but actually we can still use L'Hopital's rule if we're looking at something from the right. Now, the reason that we're looking as x approaches 0 from the right and not just as x approaches 0 is because the natural log of x does not exist at x equals 0. So we can only approach x from the positive side, okay? So actually, if I look at the graph of the natural log, maybe you remember, it kind of looks like this, right? And so essentially, as I approach 0 from the positive side, then the limit as x approaches 0 of just the natural log of x, this is actually equal to negative infinity. Okay? So then if I look at the limit as x approaches 0 from the right of, I'm going to just write cotangent as the cosine of x over the sine of x, then this gives me 1 over 0, right? Which is really an infinite situation. Whenever I have a number on top and a 0 in the denominator, that always gives me an infinite situation. So again, I have a infinity over infinity case, which means I can use L'Hopital's rule. Now this one I can't just look at and be like, oh yeah, it's going to be 4/3, right? So I'm going to really have to use my L'Hopital's rule here. So L'Hopital's rule, I'm going to take the limit as x approaches 0 from the positive side. And the derivative of the natural log of x is 1 over x. The derivative of cotangent is negative cosecant squared. All right, so before I start trying to evaluate stuff, I need to move some stuff around. So really, cosecant squared, right, is really 1 over sine squared. So really what I have here is 1 over x, and then I have a minus 1 over sine squared here. And so I want to combine this into one fraction, because this is crazy. So I'm going to multiply the top and the bottom by negative sine squared over 1. And so now the bottom, when I multiply this together, I get 1 on the bottom, and now I just get negative sine squared over x here. All right, so now, let's see. So now I'm dealing with this. Oops, I should have written the limit here somewhere. So here and here. So I still have this happening. Now, unfortunately, I'm still have a 0 over 0 case here. Now the 1 can drop away. So now I'm looking at the limit as x approaches 0 from the right of negative sine squared over x. All right, so I still really have, if I plug in 0, I have another 0 over 0 case because the sine of 0 is 0 and x, when I plug in x, it's also 0. So I can actually apply L'Hopital's rule a second and third or whatever many times I want to do. Now, if my algebra is getting worse instead of better, maybe I better check what I'm doing, but I can apply it again. All right, so let's do that again. So I'm going to write the limit as x approaches 0 from the right. Now, when I do the derivative of sine, remember that is sine of x quantity squared. I'm going to have the minus here. So when I pull down this 2, this is 2 sine of x cosine of x, and then the derivative of x is 1. All right, so now I've lost my denominator completely because now the 1 I really don't even know to write. So now I'm perfectly legal in putting 0 in here. And when I put in 0 for sine, it's 0. Cosine of 0 is 1. So I have negative 2 times 0 times 1, which in the end is 0. A lot of work to say that that was 0, but the limit as this, then this is equal to 0 because we just applied L'Hopital's rule a couple of different case times. Okay, so let's just look at a couple more examples here. Now, what I have is, oh, why my light is suddenly, there we go. Okay, so if I get carried away and I'm like, oh, okay, I'm just going to use L'Hopital's rule, right? So I'm going to say, okay, L'Hopital's rule, the limit as x approaches 2 of, I can take the derivative of the top, which is 1, over the derivative of the bottom, which is 2x, and now I can plug in my 2, and I get a fourth. Ta-da! But what's the problem here? Is I actually didn't check to see if this was a 0 over 0 or infinity over infinity case. And in fact, it's not, because when I plug in 2, right, this is one of those cases where there's nothing wrong with me plugging in 2. This function here is continuous at x equals 2. So when I plug in 2, right, I can just actually plug it in here. Remember those easy cases? And I get 3 over 4 minus 3, which actually gives me 3. So this is what the actual limit is. So what I'm trying to say is that assumptions matter, right? So L'Hopital's rule specifically says that I'm allowed to use it when I get indeterminate forms like 0 over 0 or infinity over infinity are the ones that we've just looked at. I'm not allowed to use it, right, if those don't apply, because if I try to force it to use it, I get a wrong answer because this is the right correct answer, okay? So the same kind of goes here as well, right? So if I rushed ahead here and said, okay, well, I'm going to just apply L'Hopital's rule thinking, okay, I have infinity over infinity, or I have 0 over 0, then I'm going to get negative sine of x here over 1. And when I look at that, this, actually, let me put my limit in here. This looks like it becomes 0. But actually, what I actually have here is when I plug in 0 into cosine, I don't get 0. This isn't a 0 over 0 case. This is a 1 over 0 case, which means this limit is infinite. Right? So this limit does not exist, but looking at L'Hopital's rule without making sure that I have the right circumstances kind of told me the wrong thing. It told me that the limit is 0. So, like, assumptions really matter, right? When the rule says that I can use it if it's, at this point, we've really looked at 0 over 0 or infinity over infinity cases, right? This has to be the case. It doesn't work if I get a number over 0. It doesn't work if I can just plug it in, right? I'm going to get the completely wrong thing. So when we're using these rules, we do need to make sure that we're using them appropriately.